Hi, I'm Mike Smith with SAECO, Smith and Keil Engineering Company, and what we're going to talk about now is the quality assurance and quality control test methods that we see as kind of commonplace in the industry, and kind of for the value of the contractor, kind of talk about the significance of those, and then also when we see issues with those tests, maybe shed a little light on what could be happening there. First off, I want to talk about the plasticity index test. The plasticity index, or PI test, is a test that we do for both the design phase of the project as well as construction. When we do it, when we run that test during design, we're just trying to evaluate what soils are out there and how to deal with them. When we get into construction and we're doing the plasticity index test, we're doing that because the soils or aggregate base materials on the site need to meet a certain value for the PI. There's usually a maximum PI or a range of a PI that you can get to. And then we're going to talk about some other of the field methods that we use to evaluate compaction. So with me for this segment, I have Keil Krieg. And Keil is not from an engineering background. Keil started as a technician. He's been with our company since the beginning. I thought he'd be valuable because he's been on job sites. He's seen just about every mistake made by testing labs and contractors as it relates to these test methods. But before we get into the test methods, maybe Keil, you could kind of explain some of the projects you've worked on and what you've done in your career.
Sure, thanks Mike. I began my career back in 2003, started in a laboratory washing dirt, and I didn't know why they had me washing dirt, but they were willing to pay me to do it. And as time went on, I learned a little bit more and gained some more experience, and then they transferred me out into the field. I got a job out working as a technician doing the regular density testing and concrete testing. I've been doing this for about 19 years now, and I've been on a wide range of projects. We've worked out at Palo Nuclear Power Plant, building some levees and embankments for pond storage. 256 acres on one of them was the largest. So I've been a part of some environmental cleanups. There were some spills out on the east side of the country where some embankments failed at some coal-fired power plants, and they had to go back and put that back together, and I helped them in the construction phase on that. But I've done anything from commercial to residential, your typical, some high rises, and just been a part of just about any stretch of the construction industry that you'll see on any regular basis.
Okay. And now I've spent my whole career in Arizona. Now you've worked in other parts of the country. Have you seen a lot of variability in the test procedures that are used in other parts of the country compared to here?
Not typically. The biggest difference that I'll see from that side of the country to the east side of the country to the west side of the country is the soils types. So over on the east side of the country and a little bit further south towards Louisiana, the soil is much more finer, especially in Louisiana. It was all built off of the Mississippi. So it was all of that wash that came down there. So you end up with a lot of fines. We would be excited in the laboratory when we ran across a rock. We'd go wash it off and look at it because there's a rock. So your test preparations and your soak times on that affect the test, that allow the moisture to percolate into the moisture, is different out there than it is over here. Here we're very coarse-grained material and granular, where it won't absorb a lot of water. And down on the other side of the country, you can end up with moisture contents and plasticities, and even up into the hundreds when you run into certain materials. So,
but the test methods,
test methods are at their core very similar, and they all need the same values on all the different construction sites out there.
Okay. All right, good. And then, so kind of talking first about that PI, or plasticity index test. Often it gets under a lot more scrutiny during the construction phase of the project, because inevitably you're going to, on soils in Arizona, we're going to find some clay there. So first, what size material do we run that PI test on? Are we focused on the entire range of particle sizes?
No, typically, well, the method requires that you break it down to a -40 screen. It's a very small screen. It's just a fraction of an inch. We'll break it down under that. So all the rock and all the sands gets removed for the most part from that sample, and we're just focusing on a very fine portion at the bottom of a sieve screen.
Okay.
We'll take that material and we'll moisture condition it in preparation for that test.
Okay. And then in terms of different ways, technicians run those tests, or even the way you've seen it at other labs, what are some of the things you see that, maybe some labs struggle with that produce these inconsistent results that we see from time to time?
Right. And ultimately the question is, what is the PI? Because you're running up against the maximum of your allowed value that's required in the specifications. And we end up in other comparing our results to other laboratories, or other laboratories comparing their results to ours. And a lot of the difference is in the preparation method. It's very important that they observe the specifications, and the specifications are observed to be running something that's an AASHTO method, or an ASTM method, or an Arizona Department of Transportation method. These three different tests are different amongst the ways that they're ran. So it's very important to understand which specification is to be performed, which method is to be performed. And if you were to just take one method and say, this lab versus that lab, or this technician versus that technician, what are some of the differences? A lot of the differences is that preparation of, did they allow the sample to soak as it's required or not required? Did they do a wet preparation, where you'll take a bulk sample with the rock and you'll wash the rock off and all those fines will be accounted for in this test? Or did it get broken over a screen without that rock getting the fine particles washed off of it? That'll heavily influence your results.
Okay. And then of course this equipment that we do that test, there's a calibration requirement for that as well. And
yeah, almost all the equipment in the testing world is required to be calibrated, whether it's the size of the dot on the bottom of your cup, or whether it's your groove tool and the width of the groove, because essentially we're finding the resistance of that soil coming back together. We'll put a pat in a cup, let's say, and we'll run a groove right through it. And the wetter we go, the faster it comes together on that cup. So if I have a groove tool that makes a fatter groove on it, then it's going to take longer for it to come down, and it's going to think it's a higher plasticity material. If I have a really thin groove, it's going to come together and close and think it's a really low PI. Its liquid limit is going to be lower. So you need to have the properly calibrated equipment. You need to have the proper tools to be able to do it. And you also have to have a technician that knows to think of these things and consider them for the final results of their test, and to not hold the base of it to change the impact on that crank when you're cranking that material, test.
Okay. Kind of a similar aspect of the testing relates to the sieve analysis test, because we do the sieve analysis test on multiple samples during the geotechnical or design phase of the project. But then once we get into construction, we have to run that test to confirm that maybe it's the aggregate base underneath the slab or underneath in your pavement section, it meets a certain gradation requirement as well. So sometimes those can be a source of contention on a project when you've got one lab getting different results on another. But that one can generally be solved fairly easy compared to these other tests that we're talking about. Have you seen anything you want to mention on that sieve analysis test as it relates to, either AB or some of the embankment materials that we see?
Sure, you'll have a contractor call and request a sample over here, and the QA has already sampled. And so you'll go out there, you'll take your sample, you'll take it back to the laboratory, and why is my test different than their test? And a lot of that just has to do with either the variability of the material, where you put your shovel, how the sample is prepared in the laboratory. But one of the main parts of materials testing is having a representative sample obtained from the field of what the larger sample is, which would be the product on site. So it's important that however or wherever that sample is taken, it's taken from a similar location or a similar looking location that's typical of what the other technician might have taken, to avoid any variance in the sampling location. If he gets a big rock in his, because he sampled from a rocky spot, I don't know that you'd necessarily want to go sample from the rocky spot, but it wouldn't be the same. If a contractor wanted to reduce some of those variables, they would have the QA and the QC lab sample together, or blend a sample and split it down the middle so that we could be sure that we're getting the same representation of the product that's on site.
Okay. All right, good. So what we discussed so far is some of the tests we do in our laboratory. And again, there's several laboratories in Phoenix that do them. Also, some of the government laboratories do their own testing. But we're going to kind of transition now to the test methods that we do actually on the job site. And they're mainly related to trying to verify the level of compaction that the contractor is achieving as they place moisture conditioned and compact soil. So what we're after there is there's often a minimum percent compaction. I've seen it as low as 92, as high as 98% of some laboratory reference value, which could be a modified Proctor or standard Proctor. And then when we get into the construction phase of the project, we're going out there to do a test to determine exactly what that percentage is. So one of those primary tests that we use is the nuclear density test. And I think, Kyle, if we could just start by explaining the kind of the basics of that test and some of the things that you've experienced with how that can also be misleading with some of the results you've seen on that one.
Right. To understand the nuclear density test, you kind of have to understand what the test is and how a gauge works. We go by drilling a pin into the ground and setting this device over the top of it and dropping a nuclear particle basically down into the bottom of it. That nuclear particle will be generating or giving off radioactive elements to it, and it will be received by the receiver in the nuclear gauge. So the less radiation that gets back to the receiver, the denser that it thinks it is, just as in the difference of putting it behind wood or putting it behind concrete. The more soil that you smash into that area between the radioactive particle and the receiver, it's going to tell you, it will translate that into a density. The most important thing, I believe, is making sure that these technicians or whoever's out performing these tests prepare the site properly and make sure that they're in an area that is representative of what the contractor or what it is that you're trying to sample or find the density of. If you have a contractor that's prepared a big 70,000 square foot subgrade, you don't want to necessarily go over and test if there's a puddle of water where the water truck was sitting. You're going to want to try and get the whole representative area of what the rest of the material is looking like. Prepare your surface, make sure that it's flat and not have any voids underneath that gauge. Oftentimes you'll have rutting across your subgrades where the tires are from trying to compact the material, and you'll have you'll see that someone will put a gauge down and it'll have a gap, and a space gap under that. The nuclear gauge doesn't know that a tire ran over it. It's just going to read it as less density. You want to have that surface area as flat as possible so that it's in contact and is getting and obtaining the density of all the soil that's there and not having a false result due to a void that it shouldn't be included in that test. Another thing that I'll see is that technicians, or you'll see someone pounding a pin and you'll see that the pin struggles to get through and then it breaks free. I know that a rock is under there and I might need to move my test because that will have created a void that's unseen underneath there. Mm-hmm. Every day we need to be standardizing our gauge and making sure that it re-zeroes itself out. That radioactive element in there is decaying and is dying off and reducing its size every day. So we'll need to take that and put it on a block that the gauge is gauge knows what that block's density is, and it will re-zero itself out every day. And some of the other considerations, if it here in Arizona gets really hot, and we'll standardize our gauge in the morning, and sometimes we'll have a morning shower on the rare occasion, but that humidity will highly affect the results of your gauge. You will need to probably re-standardize that in the afternoon. Once that heat comes up and you've got the humidity out there, that will definitely affect it. Another thing that will affect it that's I think very important is when you're in a trench, you take your standard outside of the trench up on the surface. There's nothing around that gauge, it's just in the open air. But when you drop a gauge down into the trench, those radioactive elements are coming out, and what it does is it has one element that bounces off a hydrogen molecule, and then that gets picked back up by the receiver. So it shoots out radioactivity that bounces off the hydrogen molecule and comes back to the receiver. If you put that gauge down in a trench, but you standardized it up here, it doesn't have the same atmosphere outside of the trench as it does inside the trench. The trench is typically, or the material's been moisture conditioned down there, so there's an evaporation that's occurring, and you can feel that oftentimes inside that trench. And that's going to start reading that moisture that's around that gauge and is kind of encapsulated within that trench. So what we'll do is we'll put our block, our standard block, back down in that trench, and we'll standardize it in the trench to account for the moisture that's in the atmosphere for that, and kind of zero itself back out. It will have a high impact on your results. Your dry density will come up and your moisture will go down if you properly do it.
Okay. And the part of the test with a nuclear density gauge is whether to do apply a rock correction to the Proctor value, and maybe you could walk us through that process as well.
Sure. The rock correction, the need for a rock correction derives from the sample that we've taken back to our laboratory and performed what we typically call a Proctor. It's a moisture density curve that tells us what the density of that soil is. But when we take that material back to the laboratory, we don't perform necessarily the compaction testing in the laboratory on the sample as it is. We will break it down over a screen and remove some rock to have some consistency with that material for our compactive effort in the laboratory. Since we've removed that rock in the laboratory and we've performed this Proctor without it, it's no longer the same material. That density, that the pounds per cubic foot that you get from the laboratory Proctor is no longer representative of what was in the field because of the rock that was removed to perform that laboratory test. So out in the field, we will take a density test in a location, and then we'll dig up that area, and we will take the soil and weigh it as a whole, and then we'll break that material over the same screen that we broke that Proctor material over in the laboratory, so that we can then mathematically reaccount for that rock back into the mix. Rock is more dense than soil typically. So when you have a Proctor value that's say 120 pounds, but we know we removed rock out of it in the field that exists, out in the field we'll need to reinsert that back in there for a max value of 100%. So it will increase that Proctor value. So that's pretty much the nuts and bolts of that one.
And then when we talk about the rock that goes into these calculations, there's variability with that too, with the specific gravity. And perhaps you could just touch on the test that we do in the lab to get the specific gravity to determine exactly how dense the rock is.
Right. All rock is not equal. A volcanic rock versus a quartz rock. Your volcanic rock is a lot more porous, it's less dense, and so if you run across that, it's going to have a different value than a river rock per se. And all of these numbers that we're going to go over are all based on a relationship of 1 with water. Water, the density of water at a certain temperature is 62.42. So, and in this instance for specific gravity, that is equal to 1. It's 62.42 pounds per cubic foot. And so what we're going to do is take the relationship of the rock to that 1 cubic foot of water. We'll take it into laboratory and we'll weigh it underwater, and it'll give us the value of say a 2.65 is a typical number here in the valley. that's 2.65 times heavier than 1 cubic foot of water. You say your lead is, I believe lead is a 10 specific gravity and your gold is a 19 specific gravity, just to kind of give you the relationship of the one being 1 cubic foot of water. So I believe that 1 cubic foot of gold is 1,100 pounds or more than 1,100 pounds. And for our specific gravity of the typical 2.65 specific gravity of rock here in Arizona, you're looking at, I believe, at 161 pounds or 165 pounds per cubic foot, approximately there. I don't have my calculator. So we're basing that density, if I have taken that rock out of my proctor in the laboratory, and now I need to reinsert rock, I also need to know how dense it is. What kind of rock is it? Is it the density, the density of the rock may have changed, or I need to know how it is from this site to that site. On that site, we might have had volcanic rock. On this site, we might have had a different kind of rock. So the numbers that go into the rock correction also include its specific gravity, which is relative to its density. Don't know if I muddied the water enough on that one, but.
No, that's good. I think it's important that we, as a contractor, know that there's some risk involved with just assuming a specific gravity, because it does change, especially when we get outside of the Phoenix area. You can see significant fluctuations in the specific gravity that we have out there. Now let's kind of talk about another way to determine the density of compacted lift of soil, and that's the sand cone density test. So the sand cone density test is another in-place density method that we'll use. It usually marries up with the nuclear density test. So Kyle, talk about some things you've seen, issues you've seen observed with that test being performed.
Maybe some variabilities that may affect test results. One big thing is just making sure that the equipment that anybody is bringing onto a job site is calibrated. You want to make sure that the values that are produced by that equipment and that by that technician out there are valid and they're still up to date. Some things could change. Those sand cones roll around in the back of trucks and can change some of the results that they give. So you would want to make sure that those items are calibrated and that their sand is calibrated. It's an acceptable sand. It meets some of the grading requirements and the methods. Everything's very well defined on how to do every one of these tests. So every one of the items involved in a test that you see go into a test require calibrations, from the scales to some of the moisture devices that are used to get moisture contents. And also technicians need to be calibrated to do proper testing. So you don't want to just send a first aid technician necessarily out onto a job site to run a sand cone. It normally doesn't end well. You'd want them to have some experience underneath their belt. When I'm performing a sand cone, I want to make sure that I don't have any equipment rolling around me. It's oftentimes a struggle to ask a contractor to stop rolling their water truck, or their sheep's foot is vibrating off in the distance, and that's really going to impact their test in a negative way. What happens is essentially the sand will consolidate, and this is typically when the sand cone has been tipped over, the hole's been dug, the sand cone is upside down and it's flowing through there. We need to make sure that there's no vibrations, because it's going to run more sand into that hole, and essentially mathematically it's going to look like there's a larger volume and less soil came out of it. It's going to affect the density results on that one a lot. Just making sure that you've prepped a proper location. Make sure that it's flat, just like with our nuclear test. You're going to want to see a flat location so that you accommodate for all of that material that is down there. So just being thorough with the testing, being thorough with the calibrations, it's all important in this test because there's so many different pieces to getting a final number for your contractor and giving them a positive result.
Yeah, and so sometimes we do the sand cone density, sometimes we do the nuclear density testing instead. And on some projects, as I alluded to earlier, sometimes if there's a quality assurance lab and a quality control lab, sometimes they can't get their numbers to match up or correlate very well. And Kyle has been involved in a project like that for the past couple weeks. So Kyle, if I could ask you, and try to be as generic as possible, like what are the things that you've been trying to work through on that project and give a few backup details so that the viewer can kind of appreciate. Because I think what you're dealing with is, if a contractor hasn't had this issue, they just haven't had it yet. They're
Right.
going to have this problem.
Well, and that gets into being as thorough as you can with these tests. You have a subgrade area with the quality control technician getting passing results, and then you have your quality assurance technician coming to the job, doing the same test in the same area, and saying that everything fails on a consistent and regular basis. QC comes through and passes it, QA comes and fails it, the contractor's not able to place the concrete that they need to place, and now it's been going for about 2 weeks trying to buy off some of these areas with and trying to bring in larger equipment, different equipment, moisture conditioning, and it's all coming back to the 2 different tests that just aren't marrying up. We start going through, is the technician qualified? That's the first and foremost. Can this guy dig a hole and give me proper results? Okay, he's an experienced guy. He's been doing this for a long time. What do I need to go to next? How does his hole look? All right, his hole is the proper size. It's the proper size, proper width, proper depth. It's clean, he's cleaning it out. All right, well then what is the next thing? Is he weighing it? Is he dropping material on his way back to the truck? You start looking at all these different factors. Is the equipment calibrated that the technician's using? If his equipment's reading a half-pound low, I guarantee you're going to start having some of these different issues. So you try to work as a team between the QA and the QC. There's got to be a little bit of independence between everyone and a little bit of
Collaboration
on it. And everyone needs to be transparent as possible to be able to root out some of these different issues that there may be. We've seen different sands on job sites. Like I said, there's a requirement for everything that goes into the test. So if he's using a sand that doesn't meet the criteria in the 1556 ASTM, and he's using one that does that affect our test? They put it in there for a reason, so I would assume that it might have an effect on our test. So it's just another one that you want to chase down and try and understand. A lot of times we'll put a nuclear gauge test, we'll take a nuclear gauge test, and then that will give us a density of that area, and then we'll take the gauge away, and right in that footprint, we'll run that sand cone. All right, is it running consistent with what the gauge is? The gauge can be off, but is our test consistently different than that gauge? If I take this gauge, if the difference between my sand cone and my gauge is always 3 pounds, if it's 3 pounds different here, it's 3 pounds different there, 3 pounds different there, we're consistently getting a consistent result. But if you can't get a sand cone that runs consistent with a gauge, it's harder to determine that. In this instance, we have one person just performing sand cones, and our laboratory is performing a nuclear density and a sand cone, so we have a little bit more data to work off of than our sand cone failed. We've been kind of tracking our variance with our nuclear gauge. Our gauge may not be 100% accurate, but it's consistently a little bit inaccurate that we're able to account for with our sand cone and properly correct that nuclear density test. So the more data you can gather, the different variables that you can look at, I mean, everything is important in that test, with as sensitive as it is in the different measurements that are being taken. So I would just recommend go through each element with your technicians, your QA or your QC, have them get together and discuss it, and have just an overall discussion about what the issue may be. And if it's something that the technician you've hired is maybe doing incorrect or wasn't proper, I mean, we need to air that out and get it out so that we can get past the issue and move on and get the construction project going.
Yeah. So with this concept, this percent compaction, you basically have in-place density, and you divide that by your laboratory density to get your percent compaction. So we're using that nuclear density or the sand cone to get the in-place density, and then we'll use the laboratory proctor to get the denominator in that equation, the laboratory density. But sometimes we don't have the luxury of having a full laboratory proctor available. Sometimes we are called out to a site and we just don't have that data available. So there's a kind of a shortcut method to obtaining the laboratory maximum dry density, It's called a 1-point proctor. And I thought maybe, Kyle, you could just kind of discuss what goes on there to produce and get an accurate 1-point proctor.
Sure. Most of the materials across the country, they all, based on the grain sizes that you'll discover in the sieve analysis, they'll all behave a certain way with compaction efforts. If I've got this much clay, this much sands, and this much gravels, it's going to give me a compaction curve. So on the 1-point proctor, they've compiled the different soils all the way from about 145 pounds per cubic foot down to 95 pounds per cubic foot. And it's a sheet with a graph, a bunch of parabolic curves on it that represent different densities and different moisture contents of different types of soils, pretty much the whole span of the different kinds of soils that you'll typically run across. And so what we will do is take an unknown soil and we will break it down a little bit, and we'll take our compaction mold and we'll compact it in our mold of a known volume. We'll take the weight on that, we'll take the moisture on that, we'll convert that into pounds per cubic foot, and we'll graph it on this chart. That chart will give us what it will fall on one of those curves or in between one of these curves. And that will give us what that typical soil's max density is. It'll tell us what its maximum density is theoretically in pounds per cubic foot based on having a moisture content and a wet density of the soil that we're looking at that we're not quite sure of what its max density is.
Okay.
One thing, Mike, that's important about the 1-point is that if you are out in the field and you do need some sort of a result or some sort of a guarantee to go based off of, that 1-point, it's not going to give you 100% accuracy. You're still going to need to take a sample back to the laboratory to get your maximum dry density or your proctor value. But with some sort of reliability, it should give you a ballpark view of what your compaction is in place. I would never pass or fail a test or assign compliance on a test area based on a 1-point, but I can at least tell the contractor, I think you're close. You might be good, or let's give it another couple hits and see if we come up on my 1-point, we're looking pretty close. And you can at least get to within a couple percent of compaction, of what the actual compaction will be once you get the lab proctor.
Yeah, good. And I think one of the most important aspects of this from a contractor standpoint is the testing laboratories, whether they be quality assurance or quality control, they really need to get the data turned around from the laboratory side and onto the project side so people can review it and be able to make decisions about maybe changing equipment or determining if something's in specification or out of specification. So that's really up to the individual laboratory to make sure their people are getting their paperwork submitted or into a database, whatever the project deems the methodology for being able to capture that data and let the project team look at it. There's nothing worse than having a project effectively complete and now everybody's just seeing some of the density test data on it and seeing that there's issues with it that could have easily been corrected while the work was taking place. So if I was a general contractor, I would also just want to make sure that both the entities know that data and any field reports that they're preparing in conjunction with that testing is submitted on a timely basis. Pretty much every project has some requirements listed for you have so many hours to turn around your test data. Some projects even have a fine mechanism in place where if you don't have your paperwork turned in say 48 hours, the contractor is going to get fined for it not being done. So there really is some cost pressure at that point on the testing laboratories to make sure that gets done. Good. Well, we hope this shed some light for you on these test procedures and give you a better understanding of how things happen in the field and what things you can be looking for as a contractor, maybe when you're not getting field density test results you're comfortable with. Thank you.